This presentation will be on a new Pore-Type based methodology for reservoir characterization and modeling of carbonate reservoirs. This new methodology is based on the global empirical relationships between pore types and reservoir parameters, and it can be integrated into a geological framework with sedimentological and diagenetic controls on reservoir quality distribution. The method can be applied in exploration, production and development scenarios, and it produces detailed input parameters to reservoir modeling and volume estimation. Sensitivity testing can be carried out on all input parameters in short time. The methodology has been successfully applied in several producing reservoirs, including 1 Russian field, 4 Iranian fields, and 4 Iraqi fields. It has also been applied in exploration, including the 22nd application round in the Barents Sea and in prospect evaluation in the Norwegian Sea. The method has been approved by BICEF FranLab in a recent audit of a producing carbonate reservoir in Iraq. The basic elements in the methodology are pore types, porosity and height above free water level. Essentially, if we know these key elements, we can predict all reservoir parameters that normally go into static reservoir models, and also many parameters that go into dynamic models. The Pore-Type classification system published by myself is applied in the model. This classification system consists of 21 pore types as summarized in the yellow table. The key elements in the Pore-Type classification are pore geometry, pore size and porosity distribution. The pore types are controlled by sedimentological and diagenetic processes and can therefore be integrated into geological models. Predictions are based on a large global database on measured carbonate reservoir properties. Here we see the geographical location of the data that go into the database. As we see, this is a global database and currently there are more than 5,000 samples in the database. The data represent most geological time periods. The parameters that can be predicted are pore types using artificial neural network, permeability, effective porosity, porosity cutoff, cementation factors, capillary pressure curves and entry pressures, saturations, free water level, and hydrocarbon volumes. Hydrocarbon volume estimation can be carried out without performing any vertical upscaling. Many of these parameters can be predicted at both ambient and confining pressures, and for most parameters a P10 to P90 prediction can be made. Both single and dual pore-type systems can be applied. There is not sufficient time to go through all of these parameters. I will therefore only present a very simplistic work process for a static reservoir model. Pore type is one of the important elements in the methodology. The pore types are defined from thin sections in cored intervals, and in uncored intervals they are predicted from wireline logs using artificial neural network. Here we see examples for 3 of the 21 pore types. Up to the right we see chalky microporosity with patchy distribution. Down to the left we see modic macroporosity. And down to the right we see interparticle macroporosity with uniform distribution. In uncored intervals, pore types are predicted from wireline logs using artificial neural network. Artificial neural network is a modeling tool to find relationships between a set of inputs and outputs. In this case, the inputs are mostly wireline logs and the outputs are pore types. The requirement for getting acceptable results are good core to log depth shift, quality controlled wireline log input data, and a reasonable amount of core with representative pore types. Given these conditions, artificial neural network may be applied to predict pore type distribution in uncored intervals. Case histories show that we typically have 70 to 80% correct prediction when we have 6 to 7 pore types in the dataset. In the middle of this slide we see two wells that have been rotated 90 degrees counterclockwise, so that depth increases from left to right. Green color indicates intervals where pore types have been correctly predicted, whereas red color indicates intervals where pore types are wrongly predicted. The first example is from the Middle Cretaceous Savak Formation in Iran. We see that in this case we have 84% correct pore type prediction. The second example is from the late Permian Kuf Formation in the Arabian Gulf. In the middle and upper Kuf we have 76% correct pore type prediction, whereas in the lower Kuf only 42% of the samples are correctly predicted. The high prediction error in the lower Kuf is due to scaling issues related to thinly bedded sequences. High heterogeneity on a decimeter scale does tend to give higher prediction error. The variable importance for each pore type can be calculated, and here we see an example for pore type 4.112 in a given field. The input parameters to the left, those with the highest bars, have the strongest impact on the prediction of this pore type. We see that the SXOT and RXOZ logs are very important for the prediction. In this particular field, pore type 4.112 has relatively high permeability, and this is reflected by relatively high water saturation and low micro-resistivity in the flushed zone. The height above the free water level is also important for many pore types. This is because there is a close relationship between pore type, porosity, saturation and height above free water level. The prediction error for each pore type is also calculated. This figure shows the prediction error for pore type 4.112. We see that whenever this pore type is present, it is correctly predicted in 74% of the dataset. When a wrong prediction is made, we can see which pore types were predicted instead. Pore types are integrated into sedimentological models in order to distribute pore types between wells. Usually there is no simple relation between pore types and depositional setting, and one pore type can occur in several different settings. Pore type distribution charts are therefore generated for each depositional setting, and these are applied to distribute pore types within each sedimentary phases. The colors in the pie charts represent different pore types, whereas the colors in the sedimentological model represent different depositional settings. By integrating pore type distribution in wells with Facies distribution maps and pore type distribution within Facies, we can populate pore types across the field. The colors in the middle right diagram represent different depositional settings. In all the other diagrams, the colors represent different pore types. By integrating porosity from wells with porosity histograms for each Facies and pore type, we can populate porosity across the field. The colors in the left diagram represent different porosities, and the colors in the upper right diagram represent different sedimentary phases, whereas the curves represent porosity. Permeability is estimated from global porosity permeability transforms for each pore type. These plots show transforms for 3 of the 21 pore types. Solid line represent expected curve, whereas the dashed lines represent the P10 and P90 curves. Using the equations on these plots, it is possible to generate a permeability prediction tool. Here we see one of the tools for predicting permeability. Permeability can be predicted based on pore type and porosity. The bar chart to the right shows the predicted permeability for different pore types at 10% porosity. The green bar shows the expected permeability, whereas the yellow bars show the 90 percentile permeability. The predicted permeabilities and the R-squared values are also given in the table to the left. The porosity can be changed by dragging the porosity slider, and the percentile can be selected by pressing the radio buttons. The predicted permeabilities are automatically updated when input values are changed. This prediction tool can only handle single pore type systems. Samples are often composed of several pore types, and my experience is that we only need to consider the two most important ones, a dominant and a subordinate pore type. For this purpose, a permeability prediction tool for dual pore type systems has been developed. From the radio buttons, we can select the dominant and subordinate pore types. The porosity can be selected by dragging the porosity slider, and the resultant predicted permeability is given in the yellow cell. By integrating the porosity distribution with the pore type distribution and applying the porosity permeability transforms, we can predict the permeability distribution across the field. Saturation prediction applies MICP-based saturation heights scaled to a hydrocarbon system. The methodology is based on a global empirical relationship between pore types, porosity, and MICP curves. Best fit equation for irreducible water saturation and MICP curves are defined for the different pore types. Permeability is not a required input as opposed to the J-function methodology. There are two equations applied for predicting the water saturation. Which one to apply depends on the pore type. Using these equations, it is possible to create tools for predicting capillary pressure curves and water saturation. This prediction tool shows the mercury capillary pressure curve for a given porosity and pore type. The green curve represents the expected curve, whereas the yellow and red curves represent the P90 and P10 curves, respectively. The porosity can be changed by dragging the porosity slider, and the predicted capillary pressure curve is automatically updated. Pore type can be selected using the radio buttons with immediate update of the curves. The mercury air capillary pressure curves can be converted to oil water and gas water curves by clicking the appropriate radio buttons. We will use the oil water as an example. The conversion from mercury air to oil water is dependent on contact angle and the surface tension, both of which can be changed by turning these dial buttons. Changes in input values give an immediate update of the capillary pressure curves. Different pressure units can be selected from these radio buttons. This is a prediction tool for water saturation. The bar chart and a table shows the predicted water saturation for each pore type at a given porosity and height above the free water level. The porosity and height above free water level can be changed by dragging the appropriate sliders. In addition to porosity, pore type and height above free water level, The water saturation is also dependent on the hydrocarbon and water densities, and on the contact angle and surface tension. Values for all of these input parameters can be changed by turning the appropriate dial buttons. The prediction tool can handle both oil and gas reservoirs, and this can be selected from these radio buttons. By integrating the porosity distribution with pore-type distribution and the height above the free water level, and by applying the water saturation equations, we can predict the water saturation distribution across the field.